In this video, we're going to be looking at topic 4H, synthetic polymers, and we're going to be focusing on the single science outcomes for IGCSE chemistry from Edexcel. So we're going to be looking at what we mean by an addition polymer and how these are formed. We'll be looking at how to actually draw out these addition polymers and be able to determine the structure of the repeat unit, the monomer and the polymer itself, and then finishing off looking at the problems with disposing of these addition polymers. So what is polymerisation? Well, polymerisation is the joining of lots of small molecules, otherwise known as monomers, to make one large molecule, which is a polymer. So the word monomer breaks down into two parts. So we have mono, meaning one, and the mer, meaning a unit. So a small molecule or a monomer is one small unit. And these will then join to make this large molecule, which again breaks down into the poly, which means many, and mer, which means unit, meaning many units joined together. Now, in this case, we're going to be looking at alkenes. Okay, this is the only substance that we will cover in terms of polymerization, and alkenes are used because they have that carbon-to-carbon double bond, so they can undergo addition reactions. Alkanes don't have that carbon-carbon bond, that's a double bond, so they can't undergo this reaction. So we're looking at alkene monomers, breaking the double bonds and then joining with each other to form one product only. So there is no side products in this reaction. The reaction will happen at very high temperatures and we need something called an initiator just to kickstart the reaction. But you're not going to be asked about this in the exam, this is just for your knowledge. And we call this process addition polymerization because we have addition reactions, so adding of units to form a polymer, which is the polymerization. So what does this actually look like? Well, what we have is we get all of our ethene monomers. So this is your ethene, which is C2H4, and we join them all up together. You can see that they're all in a row here, and we've got our double bonds. And what actually happens at this high heat and high pressure is the double bond breaks all along the chain, and we leave a single bond, so only one of the bonds breaks, and that then forms a bond with the carbon next to it. So we'll get bonds forming in the spaces. So we go from having two bonds between carbons to having one bond and then forming another bond on its left or on its right. So if you imagine you've got a row of people standing in twos holding each other's left and right hands. Those hand holding, that's your double bond. If every single group breaks one of those hand holding, they still are connected to their partner, but now they can turn and they can hold the hand of the person next to them, forming one long chain with people holding hands as opposed to being in small individual groups. This is exactly the same as what happens in polymerization. We get the breaking of this double bond and we form single bonds with the carbons next to each other, forming this very long chain. And you can see that at the sides here, we're saying that we have more and more. This is actually just a small section of the polymer, because polymer chain lengths could be upwards of 4,000 or even 40,000 carbons in a row. So of course we would never draw that, we only focus on one small section of the polymer. Now there are three key structures relating to polymers that we need to be able to identify or be able to draw. And we'll look at an example in particular, and we're going to be looking at something called polyethene. And we'll go into a bit more detail about that in just a minute. But we have a monomer structure, we have the polymer structure, and then we have something known as the repeat unit. And the good thing about this topic is that these three substances or these three structures are very, very similar. So they're very easy to relate to each other. So first of all, we're going to draw out the monomer. So we're going to have our monomer of ethene. Remember, ethene is C2H4. So I have my two carbons and I put my double bond in between. Now what I want to keep is I want to keep the sides of the carbons completely clear. So I'm going to have my hydrogens at the top and at the bottom. Don't draw out your structure like that. Okay, yes, whilst that is correct, it makes it too difficult when you're doing polymerization. You want your structure to look like a capital H, like this. So the center part is your carbon-carbon double bond, and then you have your groups that are attached to it. So I'm going to add in here. So we have that H shape. And that is our monomer. So we're showing our double bond in the monomer. When we have a polymer, what we do is we break that double bond. So I'm going to just draw exactly the same thing as I've just drawn. My only difference this time is I've got a single bond. And the way that we show the polymer is we add something known as an extension bond. And an extension bond is pretty much what it sounds like. It is a bond that extends the structure. So we're showing that this is just a small section of the polymer and that this is the part that is then going to be used. And what we do is we draw square brackets around this structure and we put the letter N outside the brackets, meaning my polymer has N amounts of this unit. And remember, N could be any number, because not every polymer is going to have exactly the same number. Now, that's the polymer. When we go to the repeat unit, that is again exactly what it sounds like. It is the unit of the polymer that repeats over and over. And all we do is we take what we've just drawn for the polymer and we remove the N and the square brackets. And that's it. So I've got my carbon with my hydrogens and my extension bonds. That is the repeat unit. So you can see that they all link together. So your monomer contains your double bond. Your polymer has got your extension bonds, your square bracket, and your N, and your repeat unit has got just your extension bonds with the single bond in the centre. But I kept everything in terms of my carbons and my hydrogens, or the groups that are attached, the same. So you can see there it's drawn out just a little bit clearer. So we've got our double bond forming our single bond, and then we've got these extension bonds. Very important to have the extension bond extending past the square brackets. That's really important in terms of the structure. And then for the repeat unit, same thing, but just not with the brackets or the letter N. Now, if we go into a bit more detail about polyethene, well, polyethene is a polymer that is formed from the monomer ethene. So what you can see when we name it, we simply take the monomer name, we put it in brackets, and then we put the word poly in front of it. That's it. So for example, if we had the monomer propene, that would form polypropene. Now, in single science, you're not expected to be able to draw this out or be able to give any information about it, but it could be a possible problem-solving style question where they ask, what could it be called? And you should use your knowledge of how you name polyethene in the same logical application. So we put the monomer's name in brackets and we put the word poly in front. So you can see that we've got the monomer and polymer that we just drew out. And there are two different types of polyethene, and you actually come across these probably in every single day of your life. So there's low density polyethene, or LDPE, and this is a very flexible polymer, and it's actually used for plastic bags or polythene bags that you would get in a supermarket. Now, the high density polyethene, or HDPE, is very rigid and very strong, and it's actually used for plastic bottles, like a milk bottle or a juice or a soda bottle. something like that tends to be made of this rigid, strong polythene. And we can recycle all of these, and you'll probably have talked about that in school when you're looking at different sustainability projects, and we'll go into a bit more detail about that in just a minute. Now, it's very common in an exam, even at single science, it's a problem-solving style question, to be asked the monomer structure from a polymer. And that can be quite a daunting question if you do get given that, because you see this huge structure that you've never seen before, and some people's first thought is to panic. What I want you to do is don't panic. It's actually much easier than you think. All you have to do is you take your structure here, so this is the polymer that we've been given, and it's polystyrene. So you've probably heard of the polymer, you just had no idea what it looked like. And all you do is you take any two carbon atoms that are together. So in this case, I'm taking this section, and I remove that from the polymer. So all I've done now to here is I've rewritten it. And this is my repeat unit. So I've got my two carbons with my hydrogens and then this C6H5 attached. And this is my repeat unit. To get to the monomer, I then remove the extension bonds and I go back to my carbon-to-carbon double bond and I make my monomer here. So this time it's going from the polymer to the monomer. So you will either be removing the double bond to get to the polymer or adding the double bond to get back to the monomer. So you might want to practice this, maybe find some examples on the internet or ask your teacher for some examples just about how to pick out the monomer. But it is much easier than you think, so don't panic if you do see a question like this in the exam. So let's do an example. We've got this polymer and we want to determine what the monomer is. So I'm going to take any two carbons that are next to each other. So I'm going to just pick these two here. I'm going to remove them to get my repeat unit. So I have my carbons with a hydrogen, a chlorine, and the two hydrogens, and then I have my extension bonds. And then to get to my monomer, I'm going to remove those extension bonds and put back in a double bond, just like that. So that's a structure you've never seen before, and now you can draw out the monomer. You're not asked to name it. That is not a requirement. It is simply, can you pick it out from this structure? Now, the last part of this topic is talking about the disposal of polymers. So most addition polymers are actually recycled. Now, you know this, that we are encouraging recycling plastic bottles, trying to cut down on single-use polythene bags, or trying to recycle bags. And the reason for this mostly is it saves on raw materials. So we want to really focus on recycling. Another major reason why we recycle is that plastics, like these polymers, are non-biodegradable. So when we're saying plastics, we are just meaning a polymer. Okay, and when we say non-biodegradable, we mean that they are not broken down by the bacteria in the environment. So if we were to dispose of a plastic bottle and just leave it outside, it is not going to decompose the way some other substances would. And this is because they have these very strong covalent bonds. So at normal temperatures, like atmospheric temperatures or your normal everyday outside temperature, they are not going to react in any way. They are inert and they are just going to remain there for years upon years. Now that's a problem. We don't want our environment or our earth to just be covered in plastic waste. So we do try to recycle them as much as possible. Now, if plastics are not recycled, there are two main ways that we dispose of them. First way is using a landfill. And a landfill is basically taking a huge hole in the ground and putting all of the plastics into it and burying them. Now, the problem with this is that landfills are quite unsightly, they don't smell particularly good, it's all rubbish, so we don't really want that, and they are still going to remain unchanged in the earth for thousands of years. So that's not really a good option for us. It does happen, but we want to avoid landfills because we are not going to be degrading it and they are going to stay unchanged. The other way that we can dispose of them is using incineration. And incineration is just another word for burning. So if we burn the plastics, we can break them down into their component parts. Now, a positive of this is that we can actually use it to generate electricity. So we can be generating some energy and put that to good use in terms of providing electricity. But the bad part of this is that it releases carbon dioxide because these are formed from hydrocarbons. So we know that when we combust a hydrocarbon, we get carbon dioxide, and that contributes to climate change and global warming. So we don't really want that. And also, for some plastics, we can actually get quite toxic gases like hydrogen chloride, and that is not a gas that we want to be breathing in. It's very bad for the respiratory system, and it is bad for the environment as well. So the best way for us to deal with our disposal of polymers is to recycle. We can use landfills or incineration, but we do want to limit that as much as possible because there are too many disadvantages to these. Recycling has the most advantages. So that should be our main focus. So remember, if you have any plastics, you want to make sure that you're recycling them. So just to summarise the advantages and disadvantages, the landfill, we don't get any greenhouse gases and it's nice and cheap, so that's a good thing, but they take up large areas of land, they don't look and smell particularly nice, no one really wants to live there, and the waste is going to be there for thousands of years. For incineration, good thing is it doesn't take up a lot of space, the burning chamber would be quite small and we don't need to spread it out. And we can produce heat or electricity for local homes and local offices. However, major disadvantages, they're expensive, they produce greenhouse gases, they release toxic gases, and any of the ash that is produced from this incineration then needs to go to a landfill site. So we're actually using both of these methods for disposal. And again, then we're going to have these same problems with landfills. So really, recycling is the way forward to be as sustainable as possible. So let's finish off by looking at a past paper question. So we're being told that ethene is being used to form polyethylene, and we've got a nice diagram here as well. So part one, what is the name given to this type of polymerization? Well, we've only looked at one type, and we call this addition polymerization. And then we want to use the diagram to state two changes that occurred during the formation of polyethylene. So we want to be referring to what's actually changing in the structure here. So first of all, we have one of the bonds and the carbon-to-carbon double bond breaks. Now remember, we don't want to say the double bond breaks, we can, but really we want to be a bit more specific and we want to be saying that the carbon-to-carbon double bond becomes a single bond or it breaks one of the bonds, so really specify that. And then what happens is we have the ethene monomers join together to form a polymer chain. So two changes, two marks, one of the bonds in the double bond breaks, and then our monomers are joining together to form that chain. And you can see that we've got some nice accepting answers here. So depending on how you word it, they will give you the mark for the double bond breaks, or it goes from unsaturated to saturated. But notice that you have to specify the word monomer or ethene joining together. So remember, in a mark scheme, if it's underlined, that word has to be included. And then the second past paper question is looking at the disposal. So the disposal for many addition polymers is a problem because they do not biodegrade. For part one, what does that mean? Well, it means that the polymer would break down, or you could say decay or decomposes. And why or how is by bacteria or microorganisms. Okay, so biodegrade means that we're getting a breakdown using bacteria or microorganisms in the environment. And what is the property that prevents the addition polymers from easily biodegrading? whereas the main fact is that they are very unreactive. Now, the fact that they're unreactive is a good thing in terms of use, because we don't want them to be reacting with whatever they're being used to store or whatever they're being used to come into contact with. But when we're disposing of them, that becomes the biggest problem, that we cannot actually react it with something very easily to break it down. So there's the mark scheme for those final questions, and you can see that we want to be very specific about some of the words that we want to be using. So that's everything for topic 4H, synthetic polymers. My biggest piece of advice here would be to practice drawing the monomer, the repeat unit, and the polymer for different examples. The one that will be focused on most in single science is polyethene, but you could be asked another as a problem-solving question, so maybe ask your teacher for some examples or have a look in the textbook. If you do have any questions, feel free to leave a comment below, and we hope to see you back soon.